This is part 2 of Unit 6, Lesson 5, the fundamental theorem of calculus and the definite integral. Okay, for the second part, we're going to talk about some special cases and also how we deal with piecewise functions. So, when we've looked at the fundamental theorem of calculus, where capital F of x is equal to the integral of f of t dt, f of t has always been the derivative of f of x. So, what if we're not sure that where f of t may or may not be the derivative? So we want to find a general rule for these expressions. So what this comes down to saying is, if you look at that second part there, why can't we say that this, taking the derivative of our antiderivative, is always equal to the composition of the function? Okay, so what we're going to do is we're going to find the antiderivative of our f of t, and then we're going to take the derivative of our f of x and see if we get back our f of t. So for some different cases. So here's the first case. Case 1 is the upper bound's a constant, and the lower bound is a function of x. But if you notice, actually that's written backwards. It should be the other way. Sorry about that, I didn't notice that before. This is the upper bound is a function of x, and the lower bound is a constant. Okay, so let's go ahead and take this antiderivative. So the antiderivative of cosine x is going to be minus sine x, or sine t, and we're evaluating it from pi to x. Okay, so using the second part of the fundamental theorem of calculus, we're going to get that f of x is equal to, this is positive. Derivative of sine is positive cosine. Is going to be sine x minus sine pi, which is of course 0. So f of x is going to be sine x. Now the question is, if we take the derivative of our capital F of x, is that going to give us our f of t, or little f of x? So we are going to take the derivative of sine of x. And if we do that, f prime of x is going to be cosine x, which is of course equal to our f of x. So in this case, we have that f of x is equal to f prime of x. So that one does work. Okay, now case 2, we're going to do where the upper bound is a function of x again, and the lower bound is a constant. But we're going to have a different result this time, so it may not work. So what we're going to do is, I know we haven't really done a derivative of this sort, but I'm just going to, or an antiderivative of this sort, but I'm just going to go ahead and do it. So f of x is going to equal 2/3 of 1 plus t to the 3/2, and we're going to evaluate this from 0 to x to the third. So f of x is going to be 2/3 of 1 plus x to the third to the 3/2 minus, putting 0 in, I get minus 2/3 times 1. And then the plus 0, so it'll just be the 1. So when I simplify this, I get f of x is equal to 2/3 of 1 plus x cubed to the 3/2 minus 2/3. So now if I take the derivative of that, I'm going to bring the power down, so I'm going to have 2/3 times 3/2, and then I lower the power by 1, so 1 plus x to the third to the 1/2, and then I take the derivative of the inside, which is going to be 3x squared. Okay, and then simplifying this, I am going to get f prime of x is going to be 2x squared times 1 plus x to the third to the 1/2 power, which is obviously not equal to our original derivative, our original function, f of x. So in this case, it does not work. So there's where you have the idea that the upper bound is a function of x and the lower bound is a constant, and one time it works and one time it doesn't. So this is a sometimes situation. Okay, so next. Now, what if both the boundaries are functions of x? So what do we do now with this one? Same idea. We're going to take the antiderivative. So capital of f of x, the antiderivative of sine, is going to be, well, let's do it this way, make it a little easier. We can use what we've used before. So let's do x squared to some arbitrary value in the interval, because we've already done when one of the boundaries was a constant. So we'll do it this way. And then this is going to go to cosine x. So that way we can use some of what we already have done, because sometimes we know that works and sometimes it doesn't. Okay, so the first one is going to be negative cosine x. You take the antiderivative of sine, you're going to get a negative cosine x. And we're evaluating that from x squared to a. Minus, instead of a plus, because that'll switch, then we're going to do the cosine x from a to cosine x. And simplifying this, we're going to get f of x is going to be minus cosine of a plus cosine of x squared. And then the next one, we're going to have minus cosine of a oops, that's the wrong spot. Let me do this in the right order. Minus cosine of x, and then that'll end up being plus a cosine of a, because you have minus and that'll be a minus. So these cancel. So f of x becomes cosine x squared minus cosine of x. And I think we can see already that this is not going to be the same if we take the derivative of that. We are going to get 2x sine minus sine okay, and then minus derivative of cosine is minus sine, and then I'll have a minus again when I take that one, so I end up with a minus. So I'll have minus sine of cosine of x, and that'll be times sine of x. So it'll look like this. It's kind of an ugly derivative. Negative 2x sine squared of sine x squared minus sine x sine of cosine of x, which doesn't look anything like the original. So that definitely is not equal to f of x. So it is possible that sometimes it will be and sometimes it won't. All right, so as you can see, in some of these, we may need our old friend, the chain rule. And so our general formula now becomes this right here. So what we have is when we're taking the derivative function, when one of the limits of integration or both the limits of integration are functions of x itself, we're going to have our chain rule here that we need. So taking the antiderivative, we have the composition of the function times the derivative of the inner function. And so what happens when we do that is that'll give us the correct antiderivative. So then when we take the derivative of our integration, we're going to have that part right here, if you notice, this section, is the same as this. But then we also add in this term, which is, this is when both limits of integration are the same, is when we also have the f of the lower limit minus the derivative of that lower limit. Okay, so let's translate this into some problems here. So find the derivative of f prime of x, given that f of x is the integral from 0 to x squared of e to t squared dt. So what we're going to find is that f prime of x, if we use the first part of what we just showed here above, we're going to have the composition, and then we're going to take the derivative of that inside function, or the upper limit there. Okay, so that's what we're going to be doing. Okay, so f prime of x is going to be e to the upper limit, so e to the x squared, and then that of course is squared because we have a squared there, and then because that's got substituted for t, so t gets substituted with x squared, times the derivative, let me put that here, of our upper limit. So simplifying this, we get 2x e to the x to the 4th power. So that's how you do those derivatives. And we'll be doing a few more of those going forward. Okay, so a few tricky ones. So evaluate this integral. And the problem is, in the first one, is that if you look at our limits of integration, this is not possible. And the reason for that, it looks like it's straightforward because you've got power rule, power rule, power rule. But 2 over x is not defined at x equals 0, which is in our interval from 6 to -3. Well, I wrote that backwards, sorry. Is from -3 to 6. 0 is a point in that interval, and it's not defined, so we can't find that. Remember, it has to be a continuous function on the interval. Okay, so let's look at our absolute value one. We haven't done any of those. And really, it's kind of a good idea to break this into pieces. So let's look at the graph of this, and what we're going to find is the x-intercept for this graph, if we look at 2x minus 5 equal to 0, happens at 5 halves, or 2.5. So if we're over here at 2.5, and we're going to cross over the y-axis like this, and then like this with a slope of 2, what we're going to find is it's probably better to break this up into two integrals, two linear integrals. So we're looking at the integration from 0 to 2.5 of the absolute value of 2x minus 5 dx. And we're going to add to that the integral from 2.5 to 4 of the absolute value of 2x minus 5 dx, because the function does two different things on either side of that vertex. So evaluating the first one, we're looking at the absolute value of x squared minus 5x, evaluated from 0 to 2.5. And let me change colors here. Plus the absolute value of x squared minus 5x, evaluated from 2.5. Let me move my page up a little bit here. 2.5 to 4. And so when I do this, I get the first absolute value will be, I'm going to have the absolute value of negative 6.25, because I'll put 0 in and put 2.5 in, and I get that, plus the absolute value, when I square 4, I get 16 minus 20, and then minus a negative 6.25, and absolute value of that, when I figure this all out, I get 8.5. Okay, so let's finish this section up with some piecewise functions. So we have a piecewise function that's made with part of a parabola when we're less than or equal to 1, and then we have a horizontal constant function when we're greater than 1. So you want to look at your limits of integration. So we are going from 3 to 8. So that would be out this way. So we are going to use this part, the constant part of the function, to find the integral. So this becomes 5x evaluated from 3 to 8, which becomes 40 minus 15. You can also write it this way. You can pull the 5 out and then just do 8 minus 3, and in both ways you get 25. So it doesn't matter which way you do it, because I haven't done one like that yet, so I figured I'd show you that one. All right, so for the next one, we're going to have to do it in 2 pieces, because we're going to have to go from -2 to 1, because that's where our break is here. And for that one, we're going to use 3x squared, because that section is a continuous function and integratable. And then we're going to add to that, going from 1, that's a terrible integration symbol, going from 1 to 4 of our constant function. Okay, so finding the antiderivative of both of these, we get x to the third, evaluated from -2 to 1, plus 5x, evaluated from 1 to 4. And when we do that, we get, have some room here, we're going to get 1 minus a -8, so 1 plus 8 for that one, plus 20 minus 5. And so we get 9. Adding that all up, we get 24. Okay? And then finally, a calculator. How about that? So let's use a calculator to do this. Okay, so for number 8, if g is an antiderivative of cosine x squared over e to the x such that f of 1 equals 1/3, find f of 0. So what we're given in this problem is our limits of integration. We have a lower limit of 0 and an upper limit of 1. So we are finding an antiderivative integration from 0 to 1 of cosine of x squared over e to the x dx. And that is, of course, going to be equal to f of 1 minus f of 0. These should actually be capital F's, not little f's. I guess I could have just made this. I guess that's fine. I could just make these little f's so it matches what's given in the problem. It's just we've been using capital F, and she switched it up by calling that G. But, okay. So I can go in my calculator and calculate that. So I'm going to show you on the Inspire, there's actually on the palette an integral symbol. For the 84, you have to go into math, and you have number 9 says the F integral. So, and it'll put the template on there. But you can find this template on the Inspire, and that's why I decided to use this one. And then you just put your lower and upper limits in. So you can put 0 and 1, and then enter your function. So we have cosine of x squared on top. And then in the bottom, we have e to the x, e to the x. And then, of course, we have our dx here. And we get this nice little number there. So I'll put that in and finish. So we get 0.59005099 has to equal our f of 1, which is 1/3, minus our f of 0. So just solving this for f of 0, we get that f of 0 is going to equal 1/3 minus 0.59005099. And putting that in a calculator, since we're using it, we can put that f of 0 is approximately equal to negative 0.2567. Okay? Then, the last one, same idea. A new unleaded gasoline is being pumped into an empty underground storage tank for the opening of a new convenience store at a rate, so that's our derivative, of 600 square root of T gallons per hour. How many gallons of gasoline can supply the delivery truck if the truck pumps for 2 hours? So we know this is our dV dt. So we can find our volume by finding from 0 to 2 hours, because it's starting from scratch, of our function. And so this one, we really don't need a calculator other than to just find a value. You don't really need to do the derivative in the calculator. So we are going to get that V is going to equal 600 times 2/3 T to the 3/2. And we're going to evaluate this from 0 to 2. So we actually get, if we simplify this, 400 times, this is going to be 2 to the 3/2 minus 0, so it's just going to be that. So we get 800 times the square root of 2 gallons. And since you are allowed to use your calculator, you can put that this is approximately equal to 1131.371 gallons. Okay, and that is the end of this section.